In this nutshell, we will investigate the general purpose input-output system, which is a single-bit digital interface controlled by 3 registers, the data direction, pin, and port registers. We will look at simple circuits, explaining the terms active high and active low, and the use of pull-up and pull-down resistors to prevent floating tri-state inputs, and give simple coding examples. And if you do find this nutshell useful, please support the channel by liking the video and subscribing. We will now look at the ATmega 2560 onboard devices. The first device, which is common to all microcontrollers, is the general purpose input-output, also known as parallel input-output. This is a single-bit digital interface that has 2 states, on, high, or off, low. The GPIO can be configured to be either an input or an output, allowing the microcontroller to either read a digital input, such as a button, or write to a digital output, such as a LED. The ATmega 2560 is an 8-bit microcontroller, thus the GPIO registers are 8 bits. Therefore, the GPIO pins are grouped into 8 bits called a port. Each port is identified by a letter, such as port A or port B. The ATmega 2560 has 86 GPIO lines grouped into 11 ports, port A through to port L. Note, there is no port I. Most GPIO ports have alternative functions, which are enabled using the onboard control registers. The circuit shown here connects buttons and LEDs to the GPIO system. From this, we can see how pull-up and pull-down resistors can be used to prevent floating inputs. PA0 has a pull-up resistor. When the button is pressed, PA0 input will be low. When the button is not pushed, the pull-up resistor will make the input high. If we look at PB7, it has a pull-down resistor. When the button 3 is pushed, PB7 will be high. When the button is not pushed, PB7 is low, pulled down by the pull-down resistor. PB3 is floating. When the button 2 is pushed, the input PB3 will be high. When the button is not pushed, PB3 is floating, neither high or low. And this can inadvertently be triggered by noise, thus floating inputs should be avoided. Active high and active low describe the state of an input or output when a component, such as a button or LED, is activated. An example of an active high input is a button connected to PB7, where PB7 is high when the button is active, i.e. pushed. An example of an active low input is a button connected to PA0, where PA0 is low when the button is pushed. An example of an active high output is PD6. When PD6 goes high, the LED becomes active, turns on. An example of an active low output is PD0. When PD0 becomes low, the LED is turned on and becomes active. Each GPIO port has 3 registers that are used to configure and control the port's operation. These are the data direction, port and pin registers. Note, the X is replaced with the letter of the port. The data direction register configures each pin on the port for either input or output, where if the bit is 0, the corresponding pin on the port will be an input. If the bit is 1, the corresponding bit on the port will be an output. An example of setting the inputs and outputs on port A is shown. Note, by default, all port pins are input. The data input register, called the pin register, stores the digital state of the external pins, allowing the program to read the logic value of any pin on the port. The data output register, called the port register, is used to set the external pins to either high or low. Note, the term port has two meanings. The first is the 8-bit grouping of the GPIO pins. The second is the port register used to control the pin outputs. Each pin on the microcontroller has a pull-up resistor that can be enabled or disabled using the data direction, port, and MCU control registers. As shown in the table, to enable the pull-up resistor, the pin must be set as an input using the data direction register, the corresponding bit in the port register is set, and the pull-up disable bit in the MCU control register is clear. We can see the MCU control register here and how bit 4 is used to enable and disable the pull-ups. We can see the internal circuitry of a single GPIO pin, showing 1 bit each of the 3 registers. Here we have the port bit feeding into the switch. The data direction register bit is used to control the switch. A 1 closes the switch, connecting the port to the external pin. A 0 opens the switch, disconnecting the port. The pin bit is always reading the input pin, no matter what the data direction is set to. And the pull-up resistor here is connected to a second switch, which is activated when the data direction bit is 0, the pull-up disable bit is 0, and the port bit is 1. This coding example of the GPIO uses a switch on pin A bit 0 to control a LED on port C bit 7. Looking at the structure diagram, we have the setup, which sets up the ports, a while one loop that repeats forever. We test the switch. If the switch is on, if that's true, we turn the LED on. If it's false, we turn the LED off. Looking at the code, the hash include brings in the AVRIO library, which holds the register names and addresses. We have the macro code for turning the LED on, LED off, and for testing the switch. We have the main void here set up, where we set up the data direction registers. We come down to while 1, repeat forever. If the switch is on, the LED goes on, else the LED goes off. I have written the code using Microchip Studio and downloaded it to the microcontroller in the Seabridge Mega Pro board. We can see it in action. If I turn the switch on PA0, the LED on PC7 goes on. If I turn the switch off, the LED goes off. This program will blink a LED on port C bit 0. For the timing delay, we use the delay millisecond function, which is stored in the util delay library. The structure diagram shows setup, where we set up the port, while one loop, and repeat forever, let on, delay, let off, delay. The program itself, we include the util delay libraries. If we're using this, we must define the CPU frequency. We do the macros for bit masking for let on, let off. Finally, we run the code set up to configure bit 0 for output on port C, while one loop forever, let on, delay, let off, delay. I have written the code using Microchip Studio and downloaded it to the microcontroller in the Mega Pro board. We can see it operating with the LED on PC0 flashing every second.